We're really excited today to be here with Blair and his team at Xanadu to talk about the future of quantum computing and how we as a simulation provider can help you accelerate towards your vision of building a scalable quantum computer. We thank you for not just being a longtime customer, but also really help push us the boundary for simulation. So I want to now start by kind of talking a little bit about high-level intro and your background and how you got into quantum computing. So to start things off, could you tell a little bit about your role at Xanadu and what do you do and what does your day-to-day look like?
Yes, I'm the head of Photonics Integration here at Xanadu, and this is the team that does the design, layout, test, and assembly of our photonic integrated circuits, which go into our fault-tolerant quantum computer. So this is a team of around 30 people, split about a third each way. And my role is really just making sure we have the individuals and contributors and the skills that we need to facilitate the development in those different areas. So lots of work on the hiring side in particular, as well as maintaining the overall cohesion of the team and making sure we're working towards the kind of overall objectives and goals that we have set within the bigger hardware team, which of course are aligned with the company mission. Our mission is to build quantum computers that are useful and available to people everywhere. And what that really means is we want to make systems which aren't just for toy problems or academia, but are actually relevant to the global community and to businesses. And also to make this as accessible as possible. So with our current systems, which are online, that means like a cloud model. For the longer term, when we have a fault-tolerant system, which is really what's needed to get real business value, that means making, scaling up those systems and making the systems deployable in the far future. And the other aspect of this is making sure that people can also program these systems and interact with these systems. So there's a large number of people working on software which works on our systems, but also the wider quantum computing community systems. We have a number of very popular open source tools which allow educators and developers to use these and understand what they can do with quantum computing.
It's really fascinating. It seems like there's a lot of parallels with what we do at Flexcompute too, like enabling a new type of simulation architecture using cloud computing. So what inspires you the most about working at Xanadu?
Yeah, so I think really, I've been here since 2018, so a number of years now. And I think day to day, it's really just the people that we have still in the team in the company. It's more than a couple of hundred full-time staff. And the dedication they have to the mission and solving these really challenging problems that we're working on is definitely something which inspires me every day. And it's really it can be very hard to kind of capture some of the challenges we've had to work through and the solutions people come up with to work on those. And this is something even when we're trying to look at prospective candidates, you'll ask someone, what's a kind of low loss photonic component, what are kind of the numbers, and then we'll tell them what we have and we're working towards. And most of the time people they're either blown away or they don't believe it's possible. And so finding the people which can really be effective in that environment is challenging but very rewarding. And everyone works, it's a very collaborative environment. So really seeing people support each other and again kind of collectively solve these problems is very, very inspiring. Quantum computing has many different physical mechanisms you can use to create qubits and to create quantum computers. So I'm not going to go into all the details around all of those, but what is unique about photonics is that you have what's known as a flying qubit. So you're not using an atom or you're not using superconductors. You're using the actual photon itself as a form of qubit, and that's again kind of moving at the speed of light in the media through the system. So that gives inherent advantages with things like clock speeds typically, but then you kind of have some complexities because you have to use a different form of quantum computing based on kind of repeated measurements and teleportation, whereas other systems you can continuously interact with a long-lived or potentially long-lived qubit. So that has advantages and disadvantages. Really, the kind of key advantage is that with these other systems, when it comes to scale, at some point, you have to kind of go out of cryostat, which most of these traditional systems are in, and build larger scale systems. And generally there'll be some kind of transducer or interposer to do this, and the most natural one is to use light. So that means that these systems have to have their qubits interact with light in some way, have that light then interact with other light or interact with qubits in a different system. And having to do this transaction can introduce bottlenecks. It can reduce connectivity, can reduce efficiency, and effectively really puts much strict performance metrics on how well those systems have to perform. So if you start with photonics, you're already in optical fiber. So that's really the benefit there. So that means there's no transduction, and you can build out a system in the same way that you can build out a data center with racks of equipment. Our particular approach is a little bit different to potentially others that people might see. So we work on what's known as continuous variable photonic quantum computing. And there's different ways to look at this, but the simplest one is that where you do the gates, which are where you do things like feed forward and you have to do error correction. We're actually doing that in chips which look very much like a coherent receiver. So it's a room temperature chip using photodiodes, and that means that those complex operations, where you need to have FPGAs and heavy kind of classical resources, that's all sitting at room temperature in a rack. And in fact, the bulk of our system is actually using room temperature integrated circuits. And that means that when we move to a regime where you have to build this data center scale system, which is what you'll have to do for the first logical, to build a logical qubits in a fault tolerant system. Once you can develop a pod and develop that infrastructure, you can scale that out like a traditional data center. And that means that in the longer term, we should have a very strong advantage. What matters the most for photonics, and there's different kind of noise models and other systems with photonics, we care most about losing photons. So you care most about photon loss. So really what you want to have is the light that as soon as you generate this quantum resource, you want it to experience the most minimum number of components as possible. We're very reliant on simulation tools, not just on the individual components, but also the kind of circuit and system level. And really, again, the overhead in kind of doing a fab run, getting chips, doing the measurements is very high. Also, the area available when you do a fab run can generally be limited. There's always competing priorities. So we definitely rely on simulations to explore parameter spaces of kind of components that have been around, also come up with new IDs and try to validate those, and really try to, again, dial in the overall optimal space so that the design for manufacturing, you're drilling the DOE to, in the end, dial in the right component, that you can kind of do that in as small area as possible with as few components as possible. And this is can be very heavy on the computation side because we care, again, very much about very low loss components. Convergence is very important. And this means that, again, if there's some systematic offset, if there's some different issues with the simulations, you don't want to wait 3 months, 6 months to find out. So I'd say that's one area where, when it comes to the individual photonic components, we rely on simulations very heavily.
It seems like you are really pushing the limits of photonic components, but at some point you do have to rely on a foundry to make them, and foundries are also kind of doing their own photonic design. They're pushing their limits. I'm curious, what helps you kind of achieve a performance that's better than theirs?
I think there has been a bit of a change in the industry in the last few years. Certainly when we were kind of smaller a few years ago, the bulk of the components in a typical PDK, I think a typical kind of PhD could come up with something better within a couple of days. I think it's a little bit different now, and particularly if you look at the platforms such as Global Foundries or Tau, where you have the heavy kind of actives integration, maybe transistors as well. There you can the processes get pretty complicated, and perhaps you can rely a little bit more on the PDK components. So, but I think the biggest issue for our team is that our requirements are just so beyond what even a typical industry needs, that really, we have to push that to get those numbers, and we do that because we care about this and we work on it day in, day out. So when it comes to actual strategies to do that, sometimes it is just throwing more compute at the problem. A lot of the time, I'd say, though, we do have to come from the ground up, and we've got some people which are very deep into coupled mode theory, diving into the literature, and just trying to find overall strategies which may be a bit more effective than what the typical components would utilize. So it's important to kind of understand, when you hit a performance wall, is it fundamentally related to the design strategy, or is it related to, again, the simulation or the actual capabilities of the foundry? By having more confidence in the simulations, again, we have worked with Flexcompute to kind of improve the accuracy, over the last couple of years in different parts of the flow, right? By having this, that allows you to maybe, in some ways, de-risk a little bit more. So, for instance, if we didn't have that confidence, maybe we'd put 3 or 4 dies on a single component. Now, in a typical full reticle, we might put 1 or 2, and then you can try some brand new designs in that new area. And by doing that, you can really accelerate the roadmap. This allows us to de-risk some of our roadmap a little bit more, and rather than running multiple runs in parallel, for example, we can, within a single reticle, explore a bigger range of components, because for those new components, we've got confidence in the simulation pipeline. So with the DOEs, we don't have to have such a large DOE space. And then this means that you can try out kind of more designs, which is maybe you're saving kind of runs, but you're also saving time because you don't have to do more measurements. You also don't have to spend the focus on running multiple runs in parallel, which can be a bit of a pain point sometimes. I think it is kind of nice to see, again, the industry going in this way, that I think the more organizations and companies which kind of collectively push, then the more resources become available to everyone, right? So, and certainly this is one area where, I think the general kind of GPU acceleration and resources around this, I think, are very beneficial. And even things like, LLMs and AI getting very popular, to me, I'm always happy because I always see, you see the new AMD or NVIDIA chip announced, and you see the memory bandwidth is 5 terabits a second, and then you think that's going to be useful for the simulations later on.
How has your approach towards doing simulation, or maybe the simulation workflow, changed over time within Xanadu and your team in particular?
Yeah, so it's like I said, I've been here since 2018, so it's changed quite a lot. When I started, we were kind of using a kind of single license, numerical license from one of our collaborators, on a university server, for a couple of months before we brought up our own kind of hardware. I think that computer has less memory bandwidth than the laptop I use now, for example. And it was a small team of just a handful of people. So, over time, this morphed in a couple of different ways. To start with, was more about just taking advantage again of like better compute resources. So we had, when we had like 3 or 4 people, we had a couple of relatively heavy EC2 instances, again running numerical, and this worked pretty well at the time. It wasn't a significant limitation, but what we did run into this issue was where we're spending a lot of time doing simulations, but then the kind of shareability, the traceability was pretty challenging. So from the beginning, we did have some simple scripts for taking GES files and then automatically kind of building simulation files. So that's something we implemented very quickly. But then beyond that, it was, how do we kind of capture all these simulations we're doing and make them easy to kind of analyze and also share with others. I think really closing the loop as quickly as you can is the most important thing that you can do. And while the simulation is one thing, in the end, the result, the real physical result is the ground truth. So, as I mentioned before, definitely the way in which we can scale out these simulations, look at a very large set of DOEs. When we do the simulations, you'll simulate many more structures than you would put in the mask, right? Right. So that means that when you get the results back in, we have, again, automated measurements of put results in this same kind of database that I was talking about on the simulation side, and then it makes it very easy to connect with the design parameters, those simulations with the measured components. And then you can kind of look at those results, and then if you see some systematic offsets from the downsampled kind of DOEs, you can use that to look at the bias offset and then try to recenter the components. So by being able to have this kind of large set of simulation resources already kind of established, it can very quickly, typically even within a single tape out, kind of for a given design concept, really kind of center that and hit the target. So there's many situations where sometimes we will go kind of completely cold and try to make a circuit without any previous fab runs. And again, that's something which allows you to close the loop more at the experimental level. But again, you can only do that if you have confidence in the simulations.
I see. And in your experience, what do you think is, typically a big hurdle for a simulation to kind of match that, the ground truth or the reality, right?
Yeah, it can vary. I think a lot of the time some of the issues you'll kind of find is that the material parameters you're starting with, like the cross-section, for example, from the foundry, the information they give you isn't really the case.
Exactly. Yeah.
And there's different reasons for this. Different kinds of measurement tools for measuring things like the refractive index, systematic offsets in the bias for certain measurements. So without doing some kind of failure analysis of cross sections beforehand, generally there's definitely some risk in doing that. If you're comparing the simulations to a given geometry, I think that's these days that isn't as much of an issue. So it's about just kind of making sure what you're simulating is actually what you have.
I see. No, that's really good to know. Yeah, that's kind of there's this really there's a lot of information you kind of need from the fabrication itself for you to build more and more accurate simulation models. And that's something that we're also working towards, is to provide our customers that kind of link so that you can actually, and also some design strategies so that you can kind of try to even guess whether or not some changing this would actually make this match with your experiment. But it seems like you have this kind of incredibly efficient process internally. Do you think that type of system that you are building has to be kind of custom to your workflow, or that's something that can be generalized?
I think it could be generalized. It's certainly, as much as we're a small team, we do try to keep the team small, so we do try to make individuals as productive as they can be. But we think, I'd say, looking at the overall strategies we have and many of the workflows we have, I think this could be deployable to a number of places. So, and I expect there's other startups doing similar kinds of things. You talk with people at conferences. I'd say these workflows, I think we're maybe a bit more refined than what might be in some places. Again, we don't have, let's say within my team, it's not like we have, various different parts of the organization doing similar things. We've got a small group of people. So the important thing is, those people having visibility and not kind of repeating things that don't need to be repeated, and also kind of not wasting time on things which they don't need to do.
Mm-hmm. I see. That's fascinating. And how much? So I guess when it comes to simulation tools, there's several dimensions, right? There's like being able to run things faster, being able to run multiple things in parallel. I guess there are a number of things that our tool offers, but I'm curious, from your perspective, what are some of the key enabling features of our products that helps you use our product in your kind of this workflow?
Yeah. So definitely the ability to kind of scale out relatively freely, I think is quite important. So, certainly if you try to launch 10,000 simulations, you'll hit what's available in VMs and things like this. But, again, when we were originally back in this numerical model, it was very, you had one license, you could only do one simulation at a time. And if you combine that with, the speed of the simulations, which has improved somewhat, but even so can still be a limitation. So by being kind of not limited by that aspect, that's very critical. The other one is also the overall simulation time for a given amount of accuracy or convergence. I think again, kind of GPU or just general acceleration, having results back in 10 minutes, half an hour means you can kind of iterate as needed, and gives you more flexibility when you kind of jump in between different activities on the design side, on the layout side, in the simulation. You can really kind of choose to engage in that rather than having to plan it out and kind of discuss with people who has the availability. It's going to take a week and just start things now. So I think that flexibility is very important.
This is switching gears a little bit, but I'm trying to understand, I guess when you are doing a design, you do have an overarching goal, like, let's say you want to get to really low loss devices. In those scenarios, where do you also kind of explore new types of algorithms? Like some of the things that we offer that I can think of is like inverse design, which surprisingly, hasn't, seen a large industry adoption for various reasons. But I'm curious if these types of strategies are something that you're exploring, and kind of just what's your viewpoint on that? Like, just basically, what's your viewpoint on utilizing novel types of optimization strategies to build, let's say, low loss photonic components?
So definitely internally, we have, what I was mentioning the software before. So we have this API that I was talking about for kind of generating the simulation files and for launching the simulations. And we also have other modules within that are focused on different optimization methods. And earlier on, we were doing things a bit more brute force, like PSO, genetic algorithm. I think these days, looking at kind of either gradient-based or Bayesian-based approaches combined with adjoint, for example.
Right.
This is something that we're looking at more and more these days. And I think the important thing is that if you just kind of treat these things purely as a black box, they can take a long time. You can end up in maybe, not in the global minima, but in kind of local minima. So if you can really connect the physics of how the component operates, then that really helps. So, being able to, let's say you're doing something like a directional coupler, kind of, if there's a correlation between gap changes and width changes, kind of, if you can put that in there, you'll really kind of converge much faster and probably end up in a global optimization.
That's a really great point. And I think that, this is something that we're also, trying to work towards is a way to give the designer an ability to add their intuition. Even when you do inverse design or adjoint optimization, there's a lot of intuition and about how things work that designers already know, and giving them a little bit of the freedom helps converge on things faster, or just also come up with better designs, right? And explore larger parameter space. So that's something that we are working on. Can you explain again how kind of Tidy3D fits in that kind of workflow? So maybe I'll just let you answer the question. Yeah, how does Tidy3D kind of fit in your overall simulation workflow?
Yeah, so there's a couple of different kind of levels. So one is, as I mentioned kind of before, this high level kind of API we have for launching simulations. There it's a bit more like a black box because we're using the same interface that we're using. For kind of, again, typically you'll create the P-cell kind of in advance, and then once that's created, you'll kind of import it into this API, launch potentially different kinds of simulations, and that's one of the different backends that we kind of have. If you need to tweak, we've got some reasonable default parameters that might be updated a little bit depending on the component. Of course, if people need to, they can kind of step in there and tweak those parameters. But that's, I'd say, a bit more of like a hands-off kind of usage, and then you launch the simulation, and the result, after it's kind of simulated and it's on the Tidy3D service, then we kind of pull it onto our own database. So there's you could say like a hands-off kind of usage. This again, we'll do this for transmission over a number of modes. Maybe you pull out the scattering matrices, and then you can use that for the circuit simulations as well. So that's kind of one regime. Another one is certainly when people are really bringing up kind of new designs for the first time, maybe kind of working purely at the P-cell, and this abstraction is a bit of a pain point, and then they really kind of work more directly, maybe in a notebook or a script directly with the Tidy3D interface, and they're, kind of utilize some of the other visualization techniques that Tidy3D has to kind of just go a slightly kind of lay it closer to the machine, and see, where things break down a little bit. Maybe there's some different definition issues in the P cell, or kind of, again, you've really got to tweak the boundary conditions of the overall kind of simulation structure to get the component operating as it should.
I see. Oh, that's really fascinating. Yeah, I think we will have a lot of features to help you with at least going from layout to simulation. And also, I don't know if you use our optimization tools, or do you write your own optimization tools?
I think mostly we're using a bit of a mix. So I think part of this workflow, it's still different aspects that are more mature. And earlier on, we were doing kind of everything hands off. Now with things like our joint, it's a little bit more tightly integrated. So we have worked with different members of the Flexcompute team to make sure the right kind of metadata and information are being output, so we can use that in our optimization. And kind of, generally you want to do that a little bit closer to the actual simulation software to take full advantage of how those modes can operate.
So I think I'm going to take a step back and talk a little bit about the industry and the technology perspectives. So what advancements in photonics excites you the most? And are there any emerging technologies that you think will significantly impact your goal of building a fault-tolerant quantum computer?
I think going to conferences like OFC, generally we'll meet with kind of vendors and see different talks. And I think what's really kind of interesting for us as a kind of company is that now, for a long time we've been pushing things like the waveguide loss and things like this. We've been hitting that drum for a few years, and what's quite compelling to see now is that things like linear pluggables, co-packaged optics, a lot of these technologies actually care a lot more about loss than they used to. Right. Energy efficiency, if you can eliminate DSP, fault error correction, which to do that you need kind of much better quality signals to start with, kind of means that there's actually more kind of areas of the industry which are kind of forcing the same conversation with our partners that we are. So that means that a lot of the development we're doing is kind of being utilized elsewhere, but also that maybe we don't have to kind of front up as much of the cost, or it helps accelerate the timelines. So I think as someone working here and kind of seeing those interactions, that's been very interesting to see. And I think again we hope that we can help the overall community move applications like this sooner. Definitely anything that kind of generates volume in a foundry, that's good for everyone, because the fabs, they only work well when they're running lots of wafers. So really kind of seeing this volume ramp is really kind of, it would be great to photonics to finally get, integrated photonics to finally get to these spaces, right? So I'd say that's one aspect. As an individual, if you look at things like, I'm very interested in kind of the tech industry in general. So seeing photonics move, within the package, hopefully solving some of these kind of, bandwidth issues, between different kind of modules or processes. I find that very compelling. And again, places like TSMC kind of finally seeming to take that a bit more seriously. I think that's very exciting. And, so if by doing that, they can enable the roadmap of, again, these accelerators to kind of move up by a number of years, that's in the end going to benefit us because it's going to unlock, resources and compute power at a more commodity scale that wasn't possible.
Yeah, that's very interesting. Especially, I think some challenges in photonics are definitely physics related. And there are others that are kind of more like advanced packaging, integration related, right? And it seems like a lot of these foundries putting in a lot of resources shows that, those are the companies that can solve the integration challenges also at scale, right? And do it really, really well.
Yeah, and from a technological standpoint, what's also very compelling to see, I'd say, getting more seriously pushed and moving into production now is hybrid bonding. So oxide and kind of copper bonding. And I think photonics, there's some people, places like IMEC, talking about using this for die-to-wafer bonding as well as wafer-to-wafer bonding. I think this is very compelling because it means that the alignment accuracy for these applications, it's very strict, a couple hundred nanometers, and also you have good quality dielectrics kind of everywhere in the process. So before, if you looked at the traditional kind of 3D packaging or 2.5D packaging solutions, maybe you'd have some polymers, you'd have other material in there, but now it's really just oxide and dielectrics, good quality dielectrics the whole way through, which means that really it opens up, I think, avenues for very large scale circuits if needed, but also more flexibility and, again, kind of mixing technologies, which for the overall industry, I think is very important.
Right. And it seems like even for your approach for photonic quantum computing, you do envision using various material platforms to achieve various functionality within that computing platform.
Yeah, certainly. Full architecture, we require devices for creating our quantum resources, which is at the moment we're using Chi3 nonlinear optics. So again, things like silicon nitride, maybe things like gallium phosphide at some point if this technology kind of matures. And then we also require electro-optics for operating low loss but fast-ish kind of switches, and of course photodiodes for doing this final kind of measurements. And these have to be very high quantum efficiency and low parasitics. Speed isn't so important now, but the parasitics are important. So, if you can get 3 5s in a stack with things like BTO or lithium iodate, have those operate at a reasonable propagation loss. These are technologies that we're kind of developing, and also I think the overall industry will definitely benefit from. So if there's more possibilities, more degrees of freedom for this hybrid integration approaches, I think it's going to make everything in the end cheaper and more accessible in the next few years.
I see. That's fascinating. So it does seem like you are also doing a lot of simulation for active devices, detectors, high-speed electro-optic devices too. Is that correct?
Yeah.
I see. That's fascinating. All right, so now on to more fun questions. So if you could kind of wave a magic wand and wanted to create a new simulation tool, what would that be, and what type of problem you would want to solve with that?
I think so. For a while, we were really hoping that there was a good finite element time domain based solution.
I see.
As a tool, just because from what we could see for things like the Galerkin method, for a given accuracy overall, at some point that's going to be kind of superior from the convergence perspective, right?
That's
but there's obviously kind of issues around kind of the memory and other challenges with kind of that kind of approach.
Sure.
But I think if in the long term, I'd be surprised if approaches like this don't start getting more kind of focus. And I mentioned it kind of earlier, but definitely if there was a way to kind of reliably simulate, if you could simulate scattering kind of effects at the same time as a full component, I think that could be pretty interesting. So for example, there's some works, I think it's like a decade old now, looking at and this is something sometimes we ask kind of interview questions, right? Let's say you take something like a directional coupler, and maybe you want to make a weak tap, and you could say, oh yeah, you just kind of change the gap, and then at some point you'll have some very weak kind of coupling. But then in those regimes, when this coupled mode coupling is 10 to the minus 3, a lot of situations you can be actually dominated by radiative coupling. So the actual scattering from the waveguides becomes the dominant coupling mechanism. It can be very tricky to dial in a design, and that's there. So I think I've never seen, so they actually showed that in an experiment, but if you could simulate something like those effects, hopefully that's not what we need to achieve what we need to achieve, because that would be a very high compute cost. But if you could have everything being able to kind of capture those effects, I think would be very interesting.
That's fascinating. So, we're no stranger to all the advancements in AI, and it seems like you touched on this a little bit, that AI is going to help you do maybe a better photonic design, or my question to you is, how do you think this kind of AI advancement is going to help you go towards your goal of building a fault-tolerant quantum computer?
Yeah, so it's probably repeating a little bit, but like I mentioned before, definitely commoditizing hardware which benefits our overall compute. I think it's important. So, in 2 or 3 years, OpenAI will have a data center worth of stuff they won't need anymore, and places like Flexcompute could probably pick up a lot of very performant hardware on the cheap, right? So I think in the short term, that's probably going to be one of the biggest impacts, just seeing those requirements kind of shift and push technologies we need out sooner. For the kind of more day-to-day individual kind of use cases, I think it can be a little. I think at this point it's still maybe a little tricky to really put your finger on, exactly how to be utilized. Definitely, internally we have kind of rules around IP and things like this. So you got to be, there's always a question of kind of cross section and the intersection with that. I think if you look at the way people are using it, definitely the kind of generally using it as to maybe accelerate things like literature searches, as kind of like a more effective assistant. And, not so much in the code generation space just yet. I think, we've also got, a very large historical set of code bases. So lots of templates, things like this, very easy to utilize. So I think if you're starting out from scratch, I think that would be a different story. If you're in a small 2-3 person kind of startup design house and you want to generate a lot of material to start with, I think that could really be a strong accelerator. But for us, we've got this maturity, so it's not as impactful there.
So I think kind of looking forward, the quantum computing platform you're building can, will impact a lot of different areas. And we believe that it will also impact the fields of doing, just physical simulation. Can you touch on a little bit on how you see quantum computing impacting just running physical simulations?
I think this is, a bit, beyond my kind of core technical expertise. So certainly, there's going to be, when we build these first systems, they can have a certain number of logical qubits, and then over time that's going to kind of scale, right? And the number of logical qubits really dictates what kind of applications you can throw at these kind of systems. So early on, if we're talking about physical simulations, definitely the things that these will be easiest to apply to are, things which are heavily kind of bound by kind of small scale quantum physics, right? So, chemistry problems, simulating molecules, proteins, small number of kind of, small proteins. I think those are really the kind of, where you're really kind of pairing, essentially like an artificial atom, right? You kind of using these qubits in a way like this. Beyond that, I think it'll evolve pretty quickly, but it's really challenging, I'd say, to kind of say what kind of in the short term, in that early phase, what physical simulations you'd be applying this technology to kind of immediately. But again, this is, I don't work on the algorithm side, so I can't comment too much.
Yeah, that's great. I think that gives us a good sense of what the future might hold in terms of quantum nanosimulation. I think I'm basically kind of done here, so I'll just do a closing question. So if you had like one takeaway or maybe a closing piece of advice that you wanted to give to someone who's starting out in quantum computing, what would that be?
In quantum computing, work on photonics, I guess.
Yeah. That's fantastic. Actually, maybe one last question is, we love, working with you guys, and I think it really helps us make our products better, push the boundaries of what we can do. I guess my question is, what do you guys love about, working with Flexcompute?
I'm glad you asked that, actually. So, we kind of, as unsurprising based on some of the things I've said earlier, but we do, we're always looking out for the software tools that can solve the problems that we have. And, sometimes it might be a technology gap. Sometimes we can find it can be a capability gap or a resourcing gap. And I think, the team at Flexcompute really has some of the kind of brightest minds in these areas, kind of maybe established open source tools already, but definitely kind of interacting with the team, kind of seeing their solutions, seeing the eagerness to kind of solve the problems. It's very invigorating, and, it's kind of a very different experience to, putting a ticket to a website and 6 months later, after 40 other people upvote it, maybe then your shoe gets kind of bobbed through. So I think the team, they're very kind of open to take on, kind of feedback around kind of challenges, technology issues, bugs. They're responsive to push out fixes, and overall, I think the features really show kind of the love for the product and make it so compelling to use. And I think that's why it's gotten so much traction in the industry in the last.
Thank you. Yeah, we really appreciate. We try to work very closely with customers like yourself, and try to really solve problems that people are facing in the real world. And I want to thank the speaker for this really wonderful and insightful conversation. I think after this conversation, we're going to go home really excited to keep working on cutting edge simulation technologies and help make our tools better for our customers like Xanadu. Thank you.